Thank you. Yeah, I was already introduced. I'm from the Applied University in Kiel, and we are actually working on powder DED. But first of all, I want to give a bit an overview about our research group in manufacturing technology. Beside additive manufacturing, we have a strong footprint in machining, as well as in welding, where, of course, you know, all of that are strong connections to powder DED. And last but not least, although in the forming technology, we have also some certain research activities. And what I have to see, whoop, 1 second. Here. Oh. Actually, what is a central point here is the machine learning approach, which in my view is getting a big power for process control, for process optimization, generally in manufacturing, and in particular in DED processes. But coming now to the topic of this session, we are talking about tooling. And here I have summarized a little bit what is it all about if we look at injection molding tools, but also investment casting tools. Actually, in the end, I want to have a uniform cavity temperature and a high cooling rate. I have just put something from literature. You see the cooling time is really the parameter where we can get the most savings from. So what we want to do now different is about multi-material or functional graded material. So I have put on the left side just the state of the art, what you can do with powder bed fusion, conformal cooling. You can have very complex cooling shapes, really getting out the heat where it is needed, but you need a cooling channel, and the cooling channel has to have a minimum diameter, that it's not getting blocked by any dirt or any other particles you have in the cooling medium. And where we want to now get one step further is that we combine conformal cooling with so-called functional graded material or multi-material. I will get there 1 or 2 slides later. But what can functional graded material offer? Actually, you have here a material with very high heat transfer, while you have here a material with very high mechanical strength. And the best is you have a transition of the two material which is seamless. So any differences in deviation, any differences in the behavior of the different temperatures which occur is getting from the characteristics also in a seamless transition. So this is a very high potential, but which kind of additive manufacturing you need for this? It's actually the powder-based direct energy deposition. Of course, you can also do it with a wire base, but this is much more rough and from our view, not that suitable for very fine structures in tooling. But I have just a bit summarized what laser powder bed fusion can deliver and what DED can deliver. And what is really from the spider graph here, also got from literature. You see the yellow line is a DED process just in the middle between the very rough but very efficient and very fast wire arc additive manufacturing, and on the other side you have the powder bed based processes, and both of them have their strengths, and maybe we should think about to combine it, but later to that. Actually, for the moment, you have the powder bed where you have to have very filigree or complex parts, and where you need very high quality parts. High quality from surface, from dimensional accuracy. While the DED can offer you high build-up rates and multi-material up to functional graded material. So, and now getting into the center of our topic today, what is about multi-material and functional graded materials. here I have an example. This is really the maximum we could do with our DED machine tool. By the way, it's an add-up beam modulo 400. You see here we have a let's say a powder nozzle with a rough larger diameter and one with a smaller diameter for the fine build up. If you look to the right, actually we can, the table is referring to the right block, we can build up functionally graded materials where we start at the bottom with 100% 316L. Then in the next layer, we reduce the 316L to 98% and mixing 2% of copper aluminum 10 to it, a copper alloy. Then we do it in the next layer in the same way until we are at 50-50 in the middle. And then we go the other way around. So at the upper part, you have then 100% copper alloy. Of course, this is not that easy like it looks. In the center, you get some cracks, you get some problems with the mix-up. But when we transfer it to practical applications, we don't have to go this high resolution. We can also go in 10% steps, and so you avoid any critical areas where you get limits of the material behavior. So you can avoid cracks, porosities, and so on. And just that you see for tooling, it's not a classical tool steel, we know that all, but it's really getting some first research work into the topic, showing that there is potential, and to really investigate what level of potential here is. We started here with a material with a 316L, it's well known from the parameter set, and we combine it with a material like copper alloy because there you have at least 4 times higher thermal characteristics or thermal conductivity. And this is now really getting into the depth of our research work, but just to give you a flavor, if you do such things, you have the problem if you increase the mixing ratio. So to the 316L, you mix more and more copper alloy, you get some non-linearities, for example, in the set level spacing, so in your distance between the nozzle and the workpiece. And that is actually, from a scientific point of view, the big challenge here. So currently we have 2 PhD works who are dealing with this. But this is actually just the depth of, to give you a flavor, what scientific depth is here behind. Also, you see here, you have a lot of parameters which you can have variations on. So, yeah, a lot of work to do. But getting now to the practical applications we have done so far. So you see here, for example, a combination, multi-material, first of all, no seamless, no functionally graded material, just multi-material. And you see, for example, combining a thermal conductivity and corrosion resistance, so having a 316L, this is built up by direct energy deposition, and putting a cooling structure on it, also showing, this is with our nozzle with a small diameter, what accuracy can be achieved. And you have here actually a freeform surface, because you have, like you see here, bended in one direction and a slight bending in the other direction. So just a demonstrator how you could use this in a corrosion atmosphere or corrosive atmosphere for cooling applications. So think about a cooling application which is here transferring the heat, and this part is in a with water cooled in a water cooled cooling system. Another application would be increased wear resistance, for example, for die casting tools. So we have mixed here 316L with Inconel. Inconel is a turbine material. I think most of you know it from different applications. We know it's very expensive, but just showing the idea, at certain points where you need the high wear resistance, putting this material in would save a lot of material, so you could afford a material which is more cost intensive, and just showing the possibilities. And you see, this is also possible. We also applied here the 10% ratio, so to avoid any challenges we wouldn't need from the product requirements regarding anomalies or crackings or porosities in the workpiece. So, and by the way, this one is 5-axis, so the shape is actually manufactured that it's turning around, and the turntable is actually moving in this direction. So this is actually also a 5-axis part. Yeah, and then getting into the 5-axis part, because in powder bed, 2.5D process, here we have a 5-axis process. First of all, for everyone of you who is coming really from the toolmaker business, interesting question, of course, what kind of diameter could you do when you want to produce a conformal cooling channel? The answer is we get down to 3 millimeters in diameter. You see rectangular holes. Round holes are a bit more difficult, so we put it with the rectangular holes. And here we have actually a demonstrator. I think, yeah, we have it here. So if you are interested, after my presentation, just stop here and look at it. We also have the cooling demonstrator. And we have just cut it off. This is the demonstrator itself. Then we just milled it, and you see this is actually the inner surface roughness we can achieve. It's not that good like powder bed, of course, but I would see there's definitely potential, even if you want to build up very fast a bigger part with cooling channels. And just to give you an idea about how this looks like, now I hope this is working out. Yeah. So this is how a DED process in 5-axis works. So this is our cooling channel we built up. And yeah, what you see, CAM programming is also a big issue here. You have to really secure that your CAM program is working properly. You need simulation capabilities. At this point, I want to thank you to OpenMind and Hypermill who is supporting us here very much. We have also a common research project. And yeah, actually, the distance of the nozzle to the workpiece is 2 millimeters. So yeah, a bit in danger to crash the part if you are not really knowing what you're doing. So, and yeah, now switching to a completely other topic, or not that completely other, but if we want to have a bone conformal cooling channel, we are in the 5-axis part. And yeah, actually you see 3 axes for the solid, and then for the cooling channel itself, we are getting to the 5-axis simultaneous part, and we are really turning here around. And this one definitely has to be done with a sophisticated CAM cycle, which we are at the moment developing, because otherwise, if you do it manually, it wastes too much time. So it's not any more cost efficient if you want to produce such parts as a contract manufacturer. So just giving you a bit the flavor, I just have to see if because yeah, now I have to get back, yeah. Because what you just saw is this kind of conformal cooling channel, so that we get by 90 degrees around the curve, and you see here green highlighted the area we just manufactured. So this is now the capability of our 5-axis machine tool, so we can go actually step by step, and just by turning the table we can manufacture such things, and combining it with a 3-axis build-up, we are very fast in it. And this leads us to our suggestion in which direction to go, because we always get in discussions about what is better, powder bed. It's already introduced into the tool making business. There are already some, or not so less experience with it. DED is quite new, but on the other side, some tool makers have both technologies. They have a DED machine tool as well as a laser powder bed fusion machine tool. And what we would propose is actually combining the strengths of both, like I said some slides before, and really saying, why not doing it in this way? DED for an efficient build-up, where I have to build up a lot of material in short time to be here cost efficient, and where relatively large cooling channels are sufficient. Where I need very detailed cooling channels, conformal cooling channels, as well as cavity geometrical features, I can produce an LPBF part built up on with DED. That's another advantage of the DED technology. You know it from spare part business. And to build up where it is necessary a multi or functional graded material, because here you can get out the heat without an additional cooling channel. That is the big advantage here. Yeah, and this is actually what we would like to propose. We are not there yet, but if you are interested in having collaboration with us, maybe you are in the powder bed field, or you're owning a powder bed machine tool and would be interested to enlarge it, to extend it, your competencies in this field, we would be happy if we get in contact. And yeah, then a little bit of advertisement at the end of my presentation. We have now a research group, 5 people working only on the DED process, starting from simulation over CAM programming and DED specific design. What is very interesting is the in-process control combined with machine learning, with artificial intelligence. I see here a huge potential for saving costs for sensors and also for getting precise information about the process for the operator, as well as for in-process control loop. Maybe not the most precise one, but I think enough precise to get a much more stable process and to see any deviation, any process anomalies right in time, so that I can correct them before I have to yeah, rework the part with the effort involved here. Yeah, and finally, or last but not least, of course, post-processing. I told it, we are also experts in machining. That is the other way, especially in tool and die making. You have to post-process the part, and also reconditioning and repair. There, all these things also apply, but with a challenge that I have always a little bit another part, because I have always another yeah, state of wear or state of repair or damaged part. So, and with this overview, I would like to end, and yeah, not forgetting, mold and die is one of our areas, marine and medicine is another one, because we also can process titanium with our machine tool, which I think is cannot everybody. So this, yeah, with this overview, I would like to end, and would invite you to ask me questions to have a discussion on. Thank you.
Thank you, Professor Mattis. Any questions? Yes.
Hello, thank you for the presentation. I'd like to ask whether you tried other materials too than 316L and copper and Inconel. Did you try other materials?
Yes, we also tried titanium, but yeah, openly speaking, the success it's still work in progress. Yeah, we would be happy to get in other materials, but yeah, we see that getting the demand for it and actually the motivation for a research project is not that simple, because it's quite a new, still a new technology, and you have to have an application in background.
Thank you.
Thank you.
Anybody else?
Thank you. Is it possible to mix materials only in the Z directions, or also in the plane of the building, printing building?
You can do it in all 3 dimensions. Of course, you have to do some work on the parameters. So you have a huge design of experiment, to say it in that way. But definitely, we want to push in this direction. But it's the same. We need the application for getting at actually the technology pull, if you want to say so. But it's possible.
Okay, okay. And there are extruders for each materials in the machines? Yes, we
have 4 powder hoppers. So theoretically, we could also do high entropy alloys. So 4 materials we could mix. So the technology of the machine tool is there, and it's a machine tool you can put in the shop floor, which is industry ready.
Okay, thank you.
You're welcome.
Anybody else? On the medical applications, is that sort of implants?
Could be. Of course, implants, if they are very filigree, you could go to powder bed. If you want to have a material transition, a seamless, then you have to go to DED. So that would be, and especially titanium.
Perfect, thank you very much. Okay, well, we are now breaking for lunch, which means you can come up and see the parts as well if you'd like to.